Hey, thanks for being willing to try this again.
Hey, sorry, I had it muted.
No worries. Let's see. We'll do this. Cool. So then you see the board okay?
Yeah.
Thanks, Bianca. Is it just, I mean, obviously there are only three of us on so far, but is it seeming like it's lagging a little bit less?
Yeah, it's a lot better so far. So,
Okay. Yeah, I'm sorry about that. We have not a very expensive internet connection. Um, so it seems like I was probably the holdup. So as much as I'd like to see all of your faces, hopefully this will work.
yeah.
This is cool. Now I can eat my cereal and not feel weird.
True.
I'm glad to facilitating the eating to be facilitating your eating of cereal.
It was funny in Boomsma's class yesterday though, like he was lagging a little bit and Mark had said that like all he heard was don't do it and then like a silence and then those are words to live by.
I wonder if I was in a more comfortable place, I'd probably try to do that, like, purposely pretend I was lagging and just drop out something that seems like it's important, just not say it. But I don't think I'm there.
Not yet.
Not yet. We'll get there. Okay. Well, it's 9 o'clock and we've got half of you. So I think maybe I'll open up with prayer and then I'll get started with your questions. So let's pray. Lord, thank you for this day and thank you for the many blessings that you've given to us. Thank you for the connections that we can continue to make through technology, even when we're otherwise isolated. And thank you for the glories of your creation that we can explore together. And just help us today as we review some of what we've talked about in pericyclic reactions. Help us to be able to see your glory clearly. We ask all these things in your name. Amen. Okay, so as usual, now this being the second time, I'm just, looking to hear what you've got questions on from chapter 24 and help you to walk through it as best as I can.
I think like I couldn't find the in the answer key. I don't think I had 34 for some reason. So I just wanted to make sure that that's correct.
Sure. Yeah, we can absolutely go through
Yeah.
that. So 34 has a bunch of different parts. So this is 24, 34. A is the first one, and you have a ring that looks like this, and then you have a double bond, sorry, going in front here. Then you have this coming out like this, and you say that it's KMNO4 and hydroxide, and you have H plus as a workup. The H plus is really just to get things into the carboxylic acid form. This is an oxidative cleavage, so it'll actually add on to this double bond at the beginning and then eliminate after that to make aldehydes on both sides of this, and then the aldehydes will be oxidized further because this is really oxidizing. So the actual product that we end up seeing is a carboxylic acid here, then the rest of the ring. And I'm going to rearrange this bond so that it's on the other side just so we have space, but we have a carboxylic acid there too. So in the ring, there are 6 carbons, and then there's 1 off the side. We should have 1, 2, 3, 4, 5, 6 carbons in this as well.
Okay.
So far, so good on A?
Yep.
Cool. Yeah, so there are a couple of ways that we can do these oxidative cleavages, but this is one of the ways that's a little bit greener. When we do potassium permanganate, though, it always oxidizes all the way up to carboxylic acids. And because it's in base, it always makes the carboxylate right away. The acid is just getting it back to the carboxylic acid. Okay. The next one that we have is 34B. 34B is now an alkyne. The alkyne can also go through cleavage, oxidative cleavage. So we have this, and it reacts under the same conditions, potassium permanganate and hydroxide, and then also acid. Now we're going to cleave at this set of carbons. So we'll still have all the way up to the oxygen on the other side, all the way up to this carbon. This carbon becomes a carboxylic acid. This other carbon gets oxidized all the way to carbon dioxide in this case.
Okay.
This carbon, most people wouldn't care about. If you have a single carbon that gets oxidized off like this, what we're really looking for is probably this longer organic portion of the chain. So far, so good on 34B?
Yes.
Cool. 34C is also an oxidative cleavage, but now using ozone. Ozone's a lot milder, and so it doesn't give us the carboxylic acids. It just gives us the aldehydes or ketones. We have, let's see, the ring, and then off of the ring, we have a double bond like this, and then those two. The ozone will add across this bond. It'll make a weird molozonid type of intermediate that then gets cleaved off. And when it gets cleaved off, it just splits this whole thing in half. So we end up with a ketone where we had, I'm going to just go back to the alkene so it's clear where that's coming from. We have a ketone right here. So where we had a double bond between carbons, we end up having a ketone there. And on the other side, we have a double bond to oxygen, and then the 1, 2, 3 carbons. So we have 1, 2, 3 carbons become 1, 2, 3 carbons, and this 6 carbon ring becomes this 6 carbon ring. Both of these will get oxidized to the carbonyl, but neither one gets oxidized all the way to the carboxylic acid. So the difference is usually if you have potassium permanganate, it always goes all the way. However many places you can oxidize will get oxidized. If you have the ozone, so that's O3, and then followed by, usually I do zinc acetic acid. People will also do dimethyl sulfide, so DMS, which is the same as this. That's what was shown in your textbook. Either of those are reducing reagents for the molozonide that's formed here, and they always give you a mixture of either aldehydes and ketones. Questions on 34C?
Nope.
Cool. 34D is actually an oxidative piece to this. So we have the same ozone at the beginning, but then the second step is peroxide. So instead of reducing the ozone piece off, you actually are able to oxidize it off. This would give you the same types of conditions that you'd have for the permanganate. And so you end up now with a ketone on this side, just like before. But this side, because it was an aldehyde before, can get further oxidized by the peroxide, and you end up with a carboxylic acid. That's for 34D. So the only difference between 34C and D is that second step. Whether you have a reducing reagent or an oxidizing reagent determines whether aldehydes show up as carboxylic acids instead. Peroxide would be the oxidizing agent. Questions on that one?
No.
Cool.
You are lagging just a bit here and there, so some things may or may not need to be repeated. So just a heads up.
Okay, yeah, thanks, Mike.
No problem.
Are there things that you want me to go through more? I can post the recording of the Zoom, but then if you're all here, that's extra time. Is it lagging to the point where it doesn't make sense and I should just record questions again?
No, I think
Sometimes it's okay. Sometimes it's a little bad, but I think for the most part, we should be good.
Okay. Let me know if that's starting to feel different for any of you. I want to make sure that like we find a way that's best for you guys.
Okay.
Okay. Any questions on 34D? Any parts that you want to follow up? Okay. 34E has a aromatic. Aromatics are generally not reactive for these types of conditions, but it does have an alkene. The alkene is reactive. We react this with osmium tetroxide and peroxide. The osmium tetroxide is what actually does the work, but we can regenerate it with peroxide. And then the second step is periodate, or periodic acid, HiO4. So this step is going to install a diol, a cis diol. This step is going to cleave it apart into the aldehydes. So what we actually see is breaking along this bond and having each of these carbons become an aldehyde. So we end up with benzaldehyde, the second best molecule, and then we have this molecule, which has the aldehyde and the ketone as well. Like peruvaldehyde is what it's called. So these are the two products of 24D. 24E. Do you have any questions on 24E?
I don't think so. At least I don't.
Thanks, Mike. Okay, and then 24F, we have another permanganate cleavage. The only difference is in 24F, we also have an alcohol. So the reactant looks like this. We're definitely going to split here along this double bond, but because permanganate is also oxidizing, it will also oxidize this position. So when we react it with the permanganate, KMNO4, and the hydroxide and H+, we're going to split along that double bond. We'll have a ketone on this side, we'll have the ketone on the other side, and then we'll have the 5-membered ring, but we'll have a ketone instead of this alcohol as well, because it's oxidizing. Other questions on 34?
No.
No.
Cool. What else you got for me?
Can you do 2447?
Yep. I think so. I haven't looked at it yet, but I hope so.
Thank you.
Okay. Oh, this is a good one. 2447 says we can do this, and we can treat it with, my daughter's outside the window, sorry. We can treat it with potassium amide and cyclopentadiene, and we end up with something that has the formula C11H10. Oh, that's C11H10. So hopefully this is something that we recognize as a pretty strong base. This is actually a reaction from chapter 22 and 23. When we do this reaction, we're actually going to end up with a benzyne intermediate. And then normally we'd add on NH3. So it's a way of getting an NH3 onto the group, getting an amine directly instead of having a Br. We'd first eliminate and then we'd add on the group. But because we go through a benzyne intermediate, that benzyne is really reactive and it's a good dienophile, and we have a diene here. So the first thing that we do is react and make a benzyne. And then the benzyne is going to react with the diene of the cyclopentadiene. We'd have this form a new bond here. We'd have this move into the back. We'd have this form a new bond between there. And so we'd end up having this cyclization reaction, a Diels-Alder type of reaction that would join this 6-carbon ring with this 5-carbon ring to give us a total of 11 carbons. It's sometimes a little bit difficult to draw something like that. The easiest way, I think, is to start with the aromatic. That's going to be all flat. I'm rotating this around about 30 degrees from where I have it drawn here. With the aromatic, we're going to join onto these 4 carbons from these 2 carbons. So I know that I'm going to have a ring that's kind of like this. But then I also know that I'm going to have this bridge here between this carbon and this carbon. So I'm going to draw that facing up like this and facing over like this, where there's a carbon right in the center there. I'm going to label that just to be clear. So now we have 6 carbons here, and we have 1, 2, 3, 4, 5. If we follow the arrows, this is the new bond that was formed here. This is the new bond that was formed here. The only thing we're missing is the bond along the backbone from that Diels-Alder reaction, this bond right here. This gives us good evidence for the benzyne intermediate because we can actually see that extra conjugation reacting in the Diels-Alder. If we had just the aromatic itself, the aromatics don't want to lose their aromaticity, and they don't generally react through the Diels-Alder reactions. Is there any follow-up on that?
Is that a triple bond on top?
Yeah, right
really
here is a
see
triple
it.
bond. So that, let me draw out the mechanism of the first step just a little bit more. So we have a really strong base, NH2 minus, really unstable, and that's going to pull off this hydrogen. That hydrogen is going to kick these electrons in here and kick out the bromine. That's what gives us the triple bond that then reacts here. Does that help to make a little bit more sense?
Perfect. Thank you.
Yeah, no problem.
And then for like the last like product at the bottom, what's in the center of the right ring?
A CH2. Let me draw that bigger.
Okay.
I don't know if that actually was any better, but it's a CH2 here.
Okay.
So it's the same as this carbon right here. If you have a ring already in the diene, then you end up having 2 rings in the Diels-Alder product. One that remains from the diene. So these are the 5 carbons that were part of the cyclopentadiene. And then another one that forms between the dienophile and the diene. So that's what these 2 bonds are. Does that make some sense?
Yeah.
Cool. Other questions on this or other questions?
What's pulling off that BR? I'm sorry.
Oh, it's
What's pulling off that
elimination
hydrogen?
reaction.
Sorry. Yeah. Okay.
So it's being pushed off rather than being pulled off. The base here is pulling off an H.
I just can't read what's up on top up there.
Sorry, one more time.
What's going to that H?
Oh, it's an NH2 minus.
Okay, I just couldn't see what that was.
Yeah, no worries. Thank you for letting me know.
Okay.
Other questions? On this or otherwise?
Could we do number 48?
Yep.
April Fools, that wasn't on it.
We can still do 48, even if it wasn't on there. I can't remember because I don't have them all written down. Would you like to still do 48, or would you like to do a different one?
Was 48 really not on it?
No, that was just a joke.
I was fooled by your April Fools.
He
I'm
still wants
sorry.
you to do it.
Okay.
But did Mark ask that?
Yeah, it was 48 was still on there.
Okay, let's do it.
I'm sorry. Okay, so this is 48 then. 48 starts with an HBr at 40 degrees Celsius. So this is a reaction we talked about way back in the first semester. When we're doing this type of addition, we can either do it under kinetic control or thermodynamic control. The idea is that we're going to first add on this H+, and it's going to add on to one of these double bonds. After that, we'll have a positive charge that is going to be either here or here, and it's going to be resonance stabilized. So after we make something like this, we could have it react at that place with the Br. That would be the kinetic product. Or we could have these electrons move over like this, and we could react the Br here instead. Both of those are possible. What we're trying to figure out is what's most likely. Generally, it's going to be most likely to have the 1,2 addition, where we add the H over here, and then on the one position over from that, we add the Br. If it's low temperature, that's again the kinetic product. And over here, we actually see the rearrangement to the more stable alkene, and then we end up with a more stable alkene formed between the two carbons, and that would be the thermal product. Thermal products generally are formed when we have higher temperatures, like this. Kinetic products usually are formed at lower temperatures. Now, this is not necessarily high enough to make it really clear that it's the thermal, but it usually suggests if we have elevated all above room temperature that we're trying for this product. So far, so good?
Yeah.
Golden.
So then the next product that we make is going to have a Br over here, and it's going to want to react with, sorry, that's product A, with cyanide. I think the actual reaction is sodium cyanide. So when we do that, the cyanide is literally just going to kick out the bromine through an SN2 reaction. So it's nothing really fancy. It's just a nucleophile and a leaving group. Levi is at the top of the stairs asking if he can help you understand about dinosaurs.
Yes.
So anyway, this is our next product. This is our B product. And it asks us to react it then with an alkene as well, or a diene. So notice that this is going to have a relatively electron withdrawing group on it. And this is our diene. Now we're looking at a Diels-Alder reaction between these two pieces. So far, so good?
Mm-hmm.
Yeah.
Okay. So when we do the Diels-Alder reaction, we are not going to have any sort of ring that we need to worry about directing this group in a certain way, but we do need to maintain this trans stereochemistry, because if these are trans to begin with, they're going to stay trans. And they're definitely going to be trans when we form, because this is always going to be in the trans form, never in the cis form, because the trans is way more stable. So we're going to have the carbons that make up this diene are going to have the electrons move to the backbone between here, and then they're going to add on to this double bond over here. On this double bond, we'll have a CH3 that comes one direction. I'll say that's up. And I'll have the cyanide that comes off in the opposite direction, like this. I realize that's relatively small, but hopefully that can still get you the right idea. So we have the 6-membered ring that's formed from the Diels-Alder reaction, these 4 carbons and these 2 carbons. one of these is pointed up, the other carbon is pointed back, it's still attached to a cyanide. This would then be our product C in that reaction sequence. Are we following so far?
Yes.
One other thing that I'd add is we'd have the enantiomer of this as well. So this is one of the possible products. We could also have this up and this down, and those would be both formed in the same likelihood. The next product that we have uses sodium hydroxide and water and heat. That's going to be a way that we can hydrolyze this piece off, or not off, we can hydrolyze it to a carboxylate rather. And so we'd say if we use sodium hydroxide, water, and heat, this piece right here, the nitrile group, will end up becoming the carboxylate. Initially, it will form the carboxylic acid, but because we're in basic conditions, it'll pretty much immediately form the carboxylate. It doesn't bother increasing this or like changing this back up to carboxylic acid, because the next reaction is with, sorry, try a different marker. We might be running into trouble here with markers. Let's see. There we go. The next reaction is with CH2N2. And then with diba. This reagent is usually run in base, but we don't need to run it in base since we already have a carboxylate. This is one of the special SN2 reactions we talked about in first semester, and it just installs a methyl at this position. So we just make a methyl ester out of this. The next step is with the diisobutyl aluminum hydride, diba. It's a reducing agent. You can't reduce the carboxylic acids very easily, but the diba can reduce relatively easily either to an aldehyde or to an alcohol. The difference is the temperature. Because this is listed at -78 degrees Celsius, we'll be able to convert this to an aldehyde by first making an ester and then making it reduce down to an aldehyde. So our product ends up looking like this. And then we still have the enantiomer here. This would be product, let's see, D, and then this would be product E. We good up to product E? Hearing nothing, I'm going to erase some of the top stuff so we can pick this up at the beginning or at the top of the board. So we have product E right here. We react it with ethylene glycol. This is one of the reactions from chapter 17 and 18. It's a protecting group that allows us to create an acetal so the aldehyde won't react like it normally does. So the product of this is like this acetal. That acetal is going to, again, protect the aldehyde and prevent it from actually reacting the way that an aldehyde would. This is product F. And then we have, after product F, we react with a furan. So this is going to react with this, and that will give us a dieno and a dienophile. So we're going to create a Diels-Alder type reaction with this. It's relatively unclear whether we'd end up with an endo or exo product. I would not expect you to be able to trace the exact stereochemistry from something this complicated, but I do want you to be able to direct regiochemistry, which is something that is detailed in some of the other homework problems. So like being able to use whether something's electron withdrawing or electron donating to predict which side they're going to react with which. In this case, we're just going to talk about this group, the tetrahydrofuran, reacting with this. So we'd have these electrons going to form a new bond here. These electrons going to form a new bond here. And these electrons going into the backbone. We'd have the same 6-membered ring here. We'd have this and then the acetal. And then over here, we'd end up with a new 6-membered ring that also has a bridging oxygen and that alkene over there. How are we doing so far? Up to G? Okay, so once we're at G, then we can react with H2 over palladium. This is a reducing condition. We talked about it, I think, mostly in chapter 19. H2 and palladium is going to reduce alkenes and alkynes pretty readily, aldehydes less readily, but we have this protected so we don't have to worry about that. It's going to essentially eliminate this, so then this is product H, rather than redrawing the whole thing. And then the final reactant is reacting with acid. Acid is going to take off this protecting group and give us back the aldehyde. And so now I will look like this. H had changed this from a double bond to a single bond. So G had a double bond, H has the single bond. On the same backbone, I took an acid and hydrolyzed off the acetal that was there before and gave us back the aldehyde. Is there anything that you'd like to talk about in more detail in that reaction sequence?
No.
Would you not erase this real quick? I'm just still trying to like make sure I have it all down.
Yeah, sorry. I can draw back up G, H, or G and H if you'd like. I was just trying to save space and time.
No, you're fine.
Okay.
This new marker is lovely.
Yeah, I'm pretty limited until we can make it out to the grocery store to a place that actually has markers. We were on house arrest pretty much right after advising day because somebody at Levi and Iris's school came down with COVID-19. So we couldn't go out to do anything for like 2 weeks because we presumably also had it or could have had it. None of us got sick, but yeah, we couldn't go to the grocery store if we were going to get other people sick.
That's crazy.
Yeah.
Don't worry, I'll deliver your groceries for you.
Oh, thank you. The 2 weeks have passed and we've gotten groceries, but I had hoped they might have markers at Aldi's, but they did not. So I'll have to go to Meijer next time.
All right, we are good to move on.
Cool. We have about 6 minutes. If we get interrupted mid-question or if you have other questions afterwards, please feel free to send them on. I can record them just like I did before. We'll try to make this work. But what do you have for me right now?
Can you do 65?
Yep,
Thank you.
no problem. 2465. Oh, this one's cool. So it has this kind of bizarre structure right here. And over like this. And then the way they have it drawn in your book is like this, but it's just a 2-carbon chain that's bridging here. The important thing in that weird Z-ness is that there's 2 carbons in the middle there. It's saying when this is heated, you end up with a compound that instead of having the structure shown has only 14 carbons, 8 hydrogens, and 2 oxygens. So hopefully it's pretty clear you're going to have these 2 oxygens. If we're trying to count up how many carbons total, we'd see 1, 2, 3, 4, 5, 6, 7 on top, 1, 2, 3, 4, 5, 6, 7 on the bottom is one way that we could think about having those 14. That's probably the most likely because those are all part of like the major ring. And then this, if we can eliminate those, that would give us the right number of carbons. If we go through a retro-Diels-Alder, we would expect to be able to move out something in a cyclohexene like this. Again, this section right here is a cyclohexene because we have 1, 2, 3, 4, 5, 6 carbons, or we could consider this a cyclohexene. It doesn't really matter which one. So we could say, we'll take these electrons, move them, sorry, not those. We'll take these electrons and move them out like this. We'll take these electrons, move them down like this, and these electrons and move them like this. That would be the opposite of a Diels-Alder reaction, or it would be a retro-Diels-Alder, and that would transform this side of the ring so that it looks like, and we'd have ethene as a byproduct. Now, the advantage of having a ring that looks like this is now this portion is completely aromatic. And so not only can we drive this forward with heat, once we've heated it up, it's really quite stable because of this aromaticity. We do the same thing on the opposite side, and we'd end up with another aromatic ring on the opposite side. Let's see. And so this is the actual product that's formed from this that has this formula then C14H8O2. You have the 7 carbons on top, 7 carbons on the bottom. You have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and you have the 2 oxygens. Again, this is driven as a retro-Diels-Alder. Heat favors the retro-Diels-Alder. It's able to take something that has a cyclohexene and convert it into the diene form and then get rid of one of the cycles and leave behind an alkene. Because this is a gas, we can help drive it forward. Because this is an aromatic, it's super reactive in that direction. We can also match this up with the NMR spectrum. The NMR spectrum has really just 2 types of peaks, I think. If I'm looking at it for the proton, we have aromatic peaks and we have carbonyl peaks. So we have a bunch of aromatics here, a bunch of aromatics here, and then we have the carbonyl. Oh, no, I'm sorry. They're both aromatic peaks. They're just 2 different types of aromatic peaks. This type and then this type. There's no carbonyl peaks in the H one because there's no H's on the carbonyl. So again, the 2 peaks are for these 2 and these 2 versus these 2 and these 2. And the carbon spectrum, it looks like there's 3 peaks, but one of those is at 77, and that's always equal to deuterated chloroform. It's a little bit hard to see, and it's been a while since we've talked about NMR. The carbon spectrum then really only has the peak that's at around 137 or so, and the one that's maybe around 130. And then the one that's super high and hard to see, that's just above 200. So there's a carbon peak here, and then there's carbon peaks in the aromatic region. You can, sorry, I said 3 peaks. There's actually 4 peaks. The one that's just between around there's a doublet in there at like 137. So you have these two peaks are probably showing up really similarly. Questions on 2465? We've got less than 1 minute, so if you do have follow-up questions on this, let me know and I can answer those. If you have other questions that you want answered, I can